July 16th, 1945. The world's first nuclear bomb is detonated in the plains of New Mexico. Through nuclear fission chain reactions, the weapon can produce tremendous amounts of energy released in an instant. The nuclear bomb is a culmination of discoveries and theories in modern physics, from Bohr's model to Chadwick's discovery of the neutron, to Walton and Cockcroft's splitting of the lithium-7 atom, to Hahn, Meitner, and Strassman's discovery of nuclear fission, and Szilard's theory of fission chain reaction. The nuclear bomb illustrates that during the period 1945 to 1960, technology is beginning to catch up with theory.
The advent of the laser was one piece of technology developed from these new discoveries in physics. The laser, as well as the maser, which predated the laser and used microwaves instead of light, were invented by physicists Charles Townes and Theodore H. Maiman. The laser works on the amplification of the emission of light. When light is amplified and focused, a beam of many photons running in parallel to each other, each with the same frequency and crests and troughs of the light waves aligned, forms a beam of light that can travel long distances, move much more energy, and is subject to less noise, meaning it's harder to interfere with. The laser has become an essential part of the technology today and has furthered our ability to discover with new sensors and data collection devices from its creation.
During this period, the utility of X-ray diffraction in crystallography became fully realized. At the microscale, where X-rays act more as particles than a wave, X-ray photons are diffracted by individual atoms and molecules. The diffraction pattern produced by the scattering of the X-rays can reveal information about the structure, location, and size of atoms and molecules. This is especially useful for studying crystalline structure through a process known as crystallography, where X-rays are diffracted through crystals and the resulting pattern is analyzed. Scientists such as Dorothy Hodgkin and Rosalind Franklin innovated in the field of X-ray crystallography by using the technique to determine the structure of organic structures. Hodgkin having studied the structure of vitamin B12 and insulin, and Franklin the structure of DNA.
Other than new technology, many discoveries were made that revolutionized the way physicists view interactions between subatomic particles.
After Dirac's discovery of the positron, the anti-electron, in 1928, the logical next step was to seek out the antiproton and the antineutron. Even in 1929, a complete periodic table of antimatter was theorized by Charles Jeannet. It wouldn't be until 1955 that Emilio Segre and Owen Chamberlain first observed the antiproton and the antineutron. Similar to the positron, the difficulty in observing the antiproton and the antineutron comes from the fact that each antiparticle annihilates itself and its inversely charged counterpart upon contact, converting each into pure energy.
Another elementary particle that was also found during this time period was the electron neutrino. First theorized in 1930 by Wolfgang Pauli to explain missing energy in a beta-minus decay interaction, in which a neutron is converted into a proton and an electron and some energy is released, now known as the electron neutrino. A team led by physicists Clyde Cowan and Frederick Rains discovered the electron neutrino's existence from presumed fluxes of neutrinos from a nuclear reactor, as well as its interaction with a large water-filled detector they had on site, in which the results had lined up with previous theories of the electron neutrino's behavior.
While we had before emphasized the importance of the tangible technological advancement brought upon by modern physics during this period, it is also important to acknowledge the advances in theory.
One such advance would be the introduction of the Feynman diagram created by Richard Feynman. Many interactions in quantum physics can be very complex to understand. The Feynman diagram was introduced to make these interactions much more simple to visualize. The Feynman diagram has now been widely adapted for use in quarks and other elementary particle diagrams.
Quantum electrodynamics was developed by Richard Feynman, Shinichiro Tomonaga, Julian Schwinger, and Freeman Dyson in 1948. Quantum electrodynamics, like so many other theories of modern physics, is a relativization of a concept of classical physics, in its case electromagnetism. It uses quantum field theory to describe light and matter and how they interact. The theory can predict the behavior of electrically charged particles with great accuracy, and is the first theory to achieve full agreement between special relativity and quantum mechanics.
Another theory developed is called BCS theory. BCS, named after physicists John Bardeen, Leon Cooper, and John Schrieffer, explains how metals become superconductive at above 0 degrees Kelvin temperatures. When a metal at this temperature has electrons flow through it, the electrons distort the lattice structure of the metal. This distortion attracts other electrons that form pairs with the distorting electrons. These pairs are called Cooper pairs. This movement of electrons dragging other electrons allows electron flow with zero resistance.
That's about all we have time for. We tried to explain as many major technologies, discoveries, and theories in physics during this time period as we could, but such is the nature of science that advancements are ongoing. Science is happening everywhere, all the time. It's impossible to include everything that happened over a 15-year span. So we implore you to look into the history of physics during this period yourself. Thank you very much for listening, and have a good day.